Hello, this is AP Chemistry Notes, pages 69 to 72. And so we're going to start looking at the equilibrium of weak acids and bases. One of the good parts about this is you should already be familiar with equilibrium and pretty good at it, because we did generic equilibrium where we did KC problems, KP problems, KSP problems, and really they all are using the same concept of equilibrium. So now when we look at Ka and Kb, you just use the same techniques that you already know. It's just being applied to a specific case here. Now, one of the nice things about when doing Ka and Kb is that it is usually the same pattern, kind of like when we did KSP. And the KSP almost always was equal to a cation times an anion, and there was no denominator in typical problems. And that was nice that it had that pattern. If you didn't see that, you knew that something was wrong. Well, it's the same here with Ka and Kb. In the case of Ka, it will always be the acid on the bottom, an H plus on the top, and the conjugate base also on top. In the case of Kb, it'll always be the base on the bottom, hydroxide on the top, and the conjugate acid. There are exceptions, but this is almost always the case, and so it's nice that we have this pattern. So when doing Ka and Kb, if you notice that you've got, for example, one thing on the top of your fraction and two things on the bottom, you probably have it upside down. Another thing that comes up is when do you use Ka and when do you use Kb? Because, for example, if you look at the system I'm looking at here, you'll see it's the same system of ammonium and ammonia. And over here we have ammonia and ammonium. Well, if you are working with the reaction on the left, this one, you are looking at a weak acid. So you would do a Ka problem. If you were looking at the equation on the right, you were looking at a weak base. So you do Kb, and you're going to want to keep that straight because sometimes problems will intentionally give you the wrong K value. In other words, they'll give you a Ka when you need a Kb and vice versa. And it's not a big deal to switch it. We'll look at that in a minute. Regarding the values, in other words, the numbers of Ka and Kb, it's like all equilibrium constants. The bigger the K, whether it's Ka, Kb, Kc, Kp, Ksp, or whatever, the more it has done, I'll just call it its thing, when it reaches equilibrium. So for example, if it's KSP, a higher KSP just means it dissolved more when it reaches equilibrium. In the case of Kc and Kp, it just means they have done their reaction more, the forward reaction as written, when it reaches equilibrium. In the case of Ka and Kb, if you were comparing weak acids, the one with the larger Ka is stronger of the two, even though they're both weak. And same with Kb. A higher Kb is a stronger base of the two. Now, it turns out there's actually a mathematical relationship between these two things, which is going to be useful. The Ka of a weak acid times, I shouldn't cover up the little times right there, the Ka of a weak acid times the Kb of its conjugate base is always going to equal 1 times 10 to the negative 14. And notice I said only conjugates. You can't take the Ka of some acid and the Kb of some random weak base. That doesn't work. They have to be a conjugate pair. So for example, we could take the system that we have up above, and we could say that the Ka of ammonia, I called it ammonia again, ammonium, I'll get it right, times the Kb of ammonia will equal 1 times 10 to the negative 14. So it would have to be, again, Ka of this and Kb of this. Another example could be the Ka of HF, hydrofluoric acid, and the Kb of F minus. They have to be that conjugate acid-base pair. And I have a little proof here showing that it works. If we take the system that we have above, here is the Ka of ammonium, and here's to the right the Kb expression of ammonia. So Ka here, Kb here. And notice if you multiply them, all this stuff cancels. The ammonia, the ammonium, and you're left with hydrogen ion times hydroxide ion. And we know what that is. We know that hydrogen times hydroxide is 1 times 10 to the negative 14. We've been using that since last year. We've not used it recently, but we did use it last year. And by the way, this is just a small side note, but this is at, I believe it's at 25 degrees Celsius. If you change the temperature of your system, this value actually changes. Just like most K values change when the temperature changes. So even though we've kind of said this is just a set number, it is an equilibrium constant. Ultimately, it's based on that. And so it does change with temperature. So that might pop up here and there, but it's pretty rare that it does. It's a more advanced type of problem. Question comes up as to what if the acid is diprotic or triprotic? Well, you have to take each hydrogen coming off as a separate equilibrium system. But if you do want the K for the whole thing, you just mathesize like we did in the equilibrium unit. So we've seen this example before. The first time I showed you this example, I was just explaining that whatever you do to the equation, you do the more extreme math. This time we're going to focus on the weak acid system here. And you can think of this as 3 related weak acids. First we have H3PO4, then we have H2PO4 with -1, and we have HPO4 with a -2. Those are 3 different weak acids that are related to each other. In some cases, they're the conjugate of each other. Well, if you write out each equation, 1, 2, and 3, you add them together. Of course, you cross out things on opposite sides like I have, and you get the overall equation that I have here. As H3PO4 losing 3 hydrogens, and you're left with a phosphate. Well, we know from before with equilibrium, if you had the K values, if I called this Ka1, Ka2, and Ka3, we know you don't add the Ks, you multiply them, but let's prove it. So here's Ka1, the expression for the first equation. And then I have it for the second equation. And then I have it for the third equation. And you'll find if we want to get this, which would be K for the overall equation, in other words, it's matching this one right here. The only way to get the 3 individual Ks, Ka1, Ka2, and Ka3 to match up is to multiply them. So I've multiplied all 3 of these. And you go through and you do the crossing out since they're being multiplied, and sure enough, it works out. And thus that proves the correct way to get the overall K of the system would be to multiply the 3 values together if you were to look them up. But we already knew this. This is just mathesized. All right, the 5% rule. So last unit, I said when you were doing common ion effect, I told you to go ahead and assume X is small. And it made the math easier. And X usually was really small. It was usually so small it didn't affect the concentration of the common ion that was already present. And of course, at some point somebody asked, well, is there a time that we can't make this assumption? And yes, there are times. I'm going to teach you that right now. It is called the 5% rule. And the idea being, if X is 5% or less than 5%, then it's considered small enough that you don't need to worry about it and you can assume it's small. However, if X ends up being bigger than 5%, that's considered too dramatic to ignore and you need to actually plug it in. So what you can do is you start by assuming X is small and you see what it turns out to be. In the case of a Ka problem, you're likely solving for H+. In the case of a Kb, you're likely solving for hydroxide. And once you solve for it, you take that value, because this would have been X. X would have equaled that, or X would have equaled that in your calculation. Divide by the initial concentration, in this case of weak acid, in this case of weak base. So this would be weak acid, this would be weak base, and you would be told it in the problem. And see, did your X value turn out to be less than 5% or greater than 5%? If it's less than 5%, you're good. Keep going. Just mention that you assumed X was small. If it's greater than 5%, you need to go back and either use the quadratic formula or do this thing called successive approximations, which I'll show you that when we do this problem. So take this example. What's the pH of 0.1 molar hydrofluoric acid? Here's its Ka, which in the world of Kas, this is actually a pretty big Ka. So of weak acids, this is a fairly potent one. So you show the equation, and for weak acids and Ka, always just take the acid, take a H+ off. In the ice chart, plug in your initial concentration. We don't have any of this or this yet. What we're solving for is this right here. We want to know what is the concentration of hydrogen ion at equilibrium. So we just did KSP problems and molar solubility, and we were focused on this X right here. So kind of forget about that for right now. We don't want that X. We want that X right there. And you fill X out in the chart. And the one that you can assume is small is this right here. It's that minus X. If X is a tiny number, subtracting it from 0.1 won't be significant. You don't have to worry about it. So here's the Ka expression for this equation. I plug my numbers in, that was given, plug my X's from the ice chart. You can assume X is small like I did right here, or you can do it over here. In fact, I'd recommend put it in the ice chart and just assume that X is small right here. Don't waste your time writing it again like I did. Do the math, and you will get an X of 0.0083 molarity. So the question now is X within or less than that 5%? So you take the 0.0083, divide by the initial concentration. In other words, the concentration that we assumed X wouldn't affect. This one over here. I put it here. Turns out this one is 8.3. In this case, you'd have to go back and fix it. This is not within the 5% rule. So you can go back. You could use this equation with the minus X and do the quadratic formula. Or like I mentioned, the technique of successive approximation works like this. You go ahead and assume X is small here. And so get rid of this. Solve for X. And then you redo your calculation with this value of X where you had minus X. So up here, you would then plug 0.0083 as your minus X. Keep these as X's because you're solving for them, and you solve it and you see what happens. And in this case, it would likely change our value of X a little bit. And then you do it again. Your new value of X, you plug in back here and do the problem again. And you keep cycling it. You keep plugging in your new X over and over until X doesn't change. It usually only takes about 2 or 3 cycles until you plug X in and you get the same value, which means you have landed on the correct value of X. We won't see this too often. We will typically be less than 5% and not have to worry about this. But there's a couple that'll pop up. So do check it. I expect you when doing these problems, at this point, when you solve for X, right here, take a moment, do the 5% check. If it is, just do that. You can just say, check, less than 5%, or something like that, and then move on with the problem. I just want you telling me that you took the time and you remember to check. All right, acid-base reactions. We could even be a little more specific here and even say that these are acid-base neutralization reactions. Neutralization reactions. We're only going to do net equations, which means we're not going to put spectator ions in because they are not doing anything. We really don't care about them. A review from last year, most teachers in first year teach it this way. They say if it's a strong acid, you just write H plus because the other ion is spectator. If it's a strong base, you just write OH minus because the other ion is spectator. If it's weak, you write the whole thing because it's not going to split that much on its own and everything will be relevant. Try to make water. And notice I wrote water in a weird way here. In this unit, it's nice when we take an H plus and an OH minus and we combine them. It's just visually satisfying to write water like that. You can write it the normal way if you wish, up to you. So you try to make water, and you usually will, but if it doesn't make water, then just stick your ions together. And you'll see that in the examples. I have, is it 5 or is there another one on the next page? No, there's 5 here. Examples, but they're all going to follow this same format that I've listed here. Just follow these steps. And just realize you've got an acid, you've got a base, and they are neutralizing each other. So in this first case, this is the classic strong acid, strong base. This is always going to look identical to this. H plus, OH minus, forming water. In the next one, I have a weak acid, strong base. You're still going to get water, and you've got this conjugate weak base that is left over from the weak acid, because it went from here to there. Next, what do we have here? Strong acid, weak base. In this case, there's no hydroxide to form water with, so you just stick them together and you get this conjugate weak acid from the weak base. Next, we've got a strong acid and a weak base that does have hydroxide, so you can make water. The question right here will come up. Do we take both hydroxides off or do we take just one off? Well, that's going to depend on what are the concentrations of this. So what's the concentration there? What's the concentration of that? That will matter. I'm assuming right now that reactions are going to completion. But without knowing these two molarities, we can't do more detail at this time. We're just looking at what's happening right now, and we'll see what happens with the changes in the amounts of chemicals that are present. And this last one, strong acid, weak molecular base. So here I have an amine. And again, no hydroxide to form water with, so just stick them together like so. And notice the amine has gained an H+, so H2 right there went to H3. And it was neutral before, but it gained a +1, so the ion has a charge of +1. Right there. Now, something you might have noticed is single one of these cases, I had a single arrow, single arrow, single arrow, single arrow, single arrow, and single arrow. There are two reasons for this. First, we're doing net equations, and the point of a net equation is to show what is happening right now. The next is, notice in every one of these cases, I had at least one strong species. So if I go through and label them, strong, strong, strong here, strong here, strong here, strong here. If you have at least one strong species, it will push the reaction forward. So it doesn't matter that the other thing is weak. The only time you would have to worry about the reaction not being pushed forward is if you were given a problem where you had a weak acid plus a weak base, and you wanted to see what was happening there. And we will look at that, but that's a more advanced problem that I don't want to bring up right now. All right, got a little practice here. I'd recommend don't write these down. So don't look at that. Try it on your own. See what you get. Just pause the video right now and try these three problems right here using what we just did, and then check your work. When you are done, you'll be back to where I am right here. Strong acid, strong base, so it's the classic. That's a gift, by the way. If I ever put one of those on a test, oh boy, you better get that one right. Strong acid, weak base, no hydroxide, so just stick them together. Weak acid, be careful, that is not sulfuric. Oh, that reminds me, we should probably review naming acids. That's sulfurous. So the naming again. If the polyatomic ion ends in 8, the acid ends in ic. So if that's sulfate, that is sulfuric acid. And if the ion ends in ite, like the one that we have here, then the acid ends in, I'm running out of room, us. So this would be called sulfurous. Sounds weird, acid. All right, weak acid, strong base. So there's my strong base, weak acid, right, the whole thing. Now, this is a case where you have to pay attention to if you were given the molarity and volume. So they said assume equal molarity and equal volume. So it's this strong species that's pushing the reaction forwards. But if these are equal amounts, I have one of these for every one of these. So if you wanted to just make it simple, just assume that it's 1 molarity and 1 liter. So I would have 1 mole of that and 1 mole of that, which means after the hydroxide has pulled off the first hydrogen to make water, we will be left with this here, and we have now run out of hydroxide. And since this is weak, it essentially is going to stay like that for the most part. In the case that you would take both hydrogens off, would be if the problem had said, let's say, forget what it says above, but let's just say that instead of it saying equal molarity and equal volume, it said you had equal volume, but let's say that this was 1 molarity and this was 2 molarity. That means that you've got double the amount of hydroxide and it would keep pulling those hydrogens off, in which case what you would do is you would have a 2 here, a 2 here, and there would be no hydrogen here. And what you would write over here is SO3 minus 2. Let me just write that out separately. I think that looks like a mess. So you would do this. H2SO3, 2 hydroxides forming 2 waters, SO4, no, SO3 minus 2. Like that. So pay attention to that. Normally these problems do say equal molarity and equal volume for simplicity. All right, looking at salts. Again, when you hear the word salt, don't just automatically think sodium chloride like in food. Salt is basically saying something ionic. So it turns out when you put something ionic in water, the resulting solution can be, we're assuming that it dissolves at least in this case, and the resulting solution can be acidic, I don't want to erase the word, or basic or neutral, and we need to be able to quickly tell. So what you want to do is look at the cation and the anion separately and see, does this cation in water make it acidic, basic, or neutral? And likewise, does the anion in water make it acidic, basic, or neutral? And add up your results here. I mentioned if you have a weak acid, if one of the ions creates a weak acid and the other ion creates a weak base, in this case, you have a competition between the two. Look up the Ka of your acid and the Kb of your base, and whoever is higher will dominate. So if the Ka is bigger than the Kb, then overall the resulting solution will be acidic. Now, the best way to learn this is what I call the NBA chart. So this is your memorizing task of this unit. Last unit, it was the precipitate rules. Now it's the NBA chart. Yeah, I call it the NBA chart because the way it's organized is we have neutral column, basic column, acidic column. And so it helps to have an order to it. I also like how anions are the top row, cations are the bottom row. So that's kind of the first thing you want to do is remember NBA across the top, and then anion and cation on the left. So these are our categories. Fortunately, you already know this entire, I can do a better job than that. You already know the entire, I guess I can't, I'm struggling on that. You know for the third time the entire neutral column. The reason is because these are the ions that are from the strong acids and the strong bases. In other words, if you have something like Cl minus coming from some ionic compound, it is not going to do anything acid or base wise, because if you did try to do something, for example, like Cl minus plus water, you'd be forming HCl like this, and that doesn't happen. HCl is a strong acid. You don't form HCl. HCl does this. It goes that way and it gives off the hydrogen. So that's why those don't happen. You'll think, oh, but there are 6 strong acids. I only see one, count like this, 1, 2, 3, 4, 5. It's because H2SO4 is a little bit more complicated, and I'll save that one for the end and explain where it's on the chart and why. And same with the strong bases. You might think, oh, the strong bases come from group 1 in senior Baca. And you go, okay, group 1, lithium, sodium, potassium, rubidium, cesium, and then senior Baca, but you don't see francium. If you want, you can include francium in this list, but often people don't bother putting francium because it doesn't exist in a significant amount. It has been found on the planet, but francium atoms are the result of radioactive decay of other isotopes, and all francium isotopes are radioactive themselves. And so if you had a chunk of francium, eventually you wouldn't have francium anymore. It would decay into something else, and there's not very much of it. I believe it's estimated that if you were to somehow gather all the francium in the entire planet, I think it's estimated that it would be about the size of a golf ball, something small like that. So there's not that much. And again, it's constantly undergoing change. So that's why you don't typically see it in charts and so forth. All right, now let's go over to the acidic column. I'm going to skip the basic column for a moment. Here, there are only 2 acidic anions, and both of them come from polyprotic acids. HSO4 comes from sulfuric, and H2PO4 comes from phosphoric. So these are 2 acids you should just be familiar with, sulfuric and phosphoric. And just know that when they lose their first hydrogen, the next remaining ion is still acidic. Now it's weakly acidic, but it is still acidic. Be careful, there are other polyprotic acids that when they lose their first hydrogen, the resulting ion is not. For example, like here, if H2PO4 minus 1 loses another hydrogen, notice this one, even though it has that hydrogen, it is considered basic. Same here, that is also considered basic. HCO3 minus 1 comes from carbonic acid. All right, down here in the acidic cations, this is actually a pretty big list because it's all the cations that weren't mentioned over here, the neutral ones. So magnesium, aluminum, ammonium, and essentially all the transitions. So iron, tin, and all the different ions, by the way. For the most part, the transition cations by themselves will be acidic. And that's going back to that thing where they form the complex ion with water, and then it's one of the waters in the complex ion that loses a hydrogen. So you need to go back to the last lesson and review that. Now, the basic cations, there are none. So, okay. The basic anions, this is the toughest part to memorize. And what I've done is I've tried to pair some of them up. So you've got HCO3 minus 1, and then if it does have its hydrogen taken, you have CO3 minus 2. So those 2 go together. Same with HS and S minus 2, and same with HPO4 minus 2 and phosphate. So when I memorized this chart, I started with those 3 pairs, and then I went through the rest. Notice I have acetate right here, but that's not the version I prefer. I actually prefer acetate to be written as CH3COO minus, because it shows Lewis structure and more useful, but either is fine. All right, now to the sulfuric acid situation. So sulfuric acid, this is strong. Once it loses that first hydrogen and you have HSO4 minus 1, that's weak. So strong acid, weak acid. And it is right here. It is acidic anion because it's a weak acid. Then, if it loses that hydrogen, you have sulfate, which you'll see is here. It's one of the basic anions. I can't put sulfate over here in the strong acids. I can't, or in the neutral anions. I can't put it like here because it's not neutral. It's basic. So that's why it's got to go over in the basic anion box. And so this one's just a little bit messier because you start with a strong acid, then you get a weak acid, and then you actually get a weak base. So that's what's happening with that. It's a special case. And then after this, I have some practice. So let's say we put sodium chloride in water. And by the way, we're assuming that everything is in water. And we're assuming that they dissolve at least a little bit. So you don't have to worry about checking solubility rules or anything like that. Obviously, if it doesn't dissolve, then there's no ions in the water to even talk about. Well, Na+, that comes from sodium hydroxide, a strong base, so it's neutral. CO-, that comes from a strong acid, so that's neutral. So neither of these ions do anything in an acidic or basic way. It's neutral. I said to write the equation if there is something happening, but there's nothing happening here. Next, again, it'd be great if you try this on your own. Stop the video. We're going to put sodium phosphate in water. See if you can figure out, using the NBA chart and what you know of acids and bases, what the resulting solution will be and why. And after you do that, then come back here and you will get, hopefully, this. Sodium is just like before, it's neutral. But now we've got this phosphate. Phosphate is in the basic part of the chart, so the solution will be basic. And the way you show that is you take the ion and you show it being a base. Well, since it doesn't have a hydroxide to give off, add water. And by the way, you always want to do that. If you're ever trying to show something acting as a base and it doesn't have a hydroxide to simply take off, add water and transfer a hydrogen to it. So notice I'm going to take a hydrogen from my water and that forms HPO4 minus 2. And what do you know? What remains of the water is a hydroxide, proving that phosphate will create a basic solution. Again, try the next one on your own. The fact that I'm giving you the Ka of something and the Kb of something else probably means you're going to have to use them. I don't typically give them just to trick you. And in this case, here's what happens. Ammonium is acidic, F- is basic. So now we have to see who's going to dominate. Well, it turns out 10 to the negative 10 is a bigger number than 10 to the negative 11. So the Ka wins. So since Ka is winning, it's going to be acidic. To show that, you take the ammonium and show it being an acid. So take off a hydrogen, like so. Notice my arrows with these are double because this will be an equilibrium system because everything's weak. We don't have anything strong like we did in the examples earlier when we were doing net equations. This is different. This is not a net equation. This is just us showing how something is acidic or basic. And then one more, CuCl2. Again, try it on your own. come back here, you're back here, or you never tried it. This one I saved for the end because it's a little bit tricky. Cu plus 2 is acidic because it's a transition cation. Cl minus is neutral, so we can ignore it. We know it's going to be acidic. And to show that, at first, when you look at Cu plus 2, you think, how can this be an acid? There's no hydrogen. It's not HCu plus 2. So you have to go back to our prior lesson. You have to look at how can things be acidic. Well, when Cu plus 2 is in water, it forms a complex ion, double the ligands, and you get this complex ion here. And it is the complex ion right here. I'm using a new color to emphasize it. The purple, that gives off a hydrogen. And that's why it forms a acidic solution. And I mentioned this in the last lesson, that when we do a lab, if I leave this stuff on the balance, it actually starts reacting with the metal tops of the balances because it is acidic and it grabs moisture from the air. I figure if there was no moisture in the air, it'd probably be okay, but there always is moisture in the air, and that ultimately leads to an acidic solution, and that then reacts with metals because acids are typically known to react with metals. We'll actually look at that reaction in detail next unit when we do reduction oxidation reactions. That's pretty much it for this lesson, but I do want to talk about these 4 systems. You'll find that we, in this unit, and exams and examples, they will use these 4 systems, especially the first 3 a lot. So the ammonia system, a problem might be based on one or both of these. That's a very common one. You've already seen it a couple times in this lesson. The hydrofluoric acid fluoride ion system is very common because not only is it a weak acid, but it's a fairly potent weak acid. So it's significant. Phosphoric acid and its relatives. So phosphoric acid, dihydrogen phosphate, hydrogen phosphate, and phosphate. That's another common system, and we are going to study this system in incredible detail in a future lab. And I say maybe this last one. This one's not very important right now. Here we have acetic acid and acetate. It's not going to be super important now, but it's a classic problem when we get to our last lesson in acids and bases, which is going to be on a topic called buffers. This is just a great example, and you'll see it mentioned when talking about buffers a lot. So it's just useful to be familiar with these 4 systems. It'll make you more comfortable. And that will do it for this lesson.